Every chip in your phone, your laptop, and every data center on Earth is built on the same foundation that engineers have used for 60 years: silicon. And in May of 2026, a team out of Nanjing University, working with Huawei Technologies, switched it off and built a working computer without it. This isn't a concept video or a press release. It's a peer-reviewed processor published in the journal Nature Electronics that runs real logic on a material that isn't silicon at all. And the reason this matters goes far beyond a lab curiosity. Silicon is hitting a wall it cannot engineer its way past. The country that solves what comes after silicon doesn't just win a research paper, it wins the next 60 years of computing. So today, we're breaking down exactly what this chip is, how it actually works, and why the timing of this breakthrough is not a coincidence. Let's start with the wall itself, because you need to understand why silicon is in trouble before you can understand why this matters. A modern transistor is, at its core, a switch. A gate sits above a channel and decides whether current flows through it or not. For decades, shrinking that channel made chips faster, cheaper, and more efficient. But somewhere below 5 nanometers, and especially below 3 nanometers, that relationship breaks down. The channel gets so thin and so short that the gate starts losing its grip on it. Electrons stop behaving like a current you can switch on and off, and start tunneling straight through the barrier that's supposed to stop them, whether the gate wants them to or not. This is quantum tunneling, and it isn't a design flaw you can patch, it's physics. The industry's answer has been gate-all-around architecture, where the gate wraps completely around the channel instead of just sitting on top of it to claw back some of that lost control. It works, but it's brutally expensive. A modern wafer using this approach can require over 1,000 processing steps, and it still relies on extreme ultraviolet lithography machines that only one company on the planet, ASML of the Netherlands, knows how to build. Engineers at TSMC, Samsung, and Intel all agree on the same uncomfortable conclusion. Three-dimensional silicon architecture has reached a point of diminishing returns. The official roadmap body for the global chip industry, the International Roadmap for Devices and Systems, says it plainly. To get meaningfully past the 1 nanometer node, the industry has to stop thinning three-dimensional silicon and start building with something fundamentally thinner. Two-dimensional materials, just a few atoms thick. So if silicon is out, what replaces it? This is where molybdenum disulfide enters the story. Molybdenum disulfide is a layered crystal, one molybdenum atom sandwiched between two sulfur atoms, that naturally peels apart into sheets under 1 nanometer thick. Graphene gets more headlines, but graphene has a fatal flaw for computing. It has no band gap, which means you can't properly switch it off. Molybdenum disulfide does have a band gap. In its single-layer form, it switches cleanly, the way silicon does, but it does it at a thickness silicon could never survive at. Because the channel is so thin, the gate can grip the entire depth of it at once, which suppresses the leakage and tunneling problems that are strangling silicon at small scales. And because the material has no dangling chemical bonds sticking out of its surface, you can stack it, layer transfer it, and integrate it in 3 dimensions in ways bulk silicon physically cannot do. On paper, this is close to a perfect successor. In a lab, on a single transistor, it has looked incredible for years. The open question that's haunted this field for over a decade has never been, can one transistor work? It's, can you build a real, multi-transistor system out of this stuff without it falling apart? That's the question Nanjing University and Huawei just answered. Here's what they actually built. It's called the Magic 1000 platform, short for Molybdenum Disulfide Advanced Next Generation IC 1000, also referred to inside China as Mengqi 1000. It is a functional 4-bit parallel microprocessor, fabricated on a custom hybrid production line, and it is not a single demo transistor. It is a real, working chip with 1,433 individual molybdenum disulfide transistors integrated onto a single die, forming 975 logic gates. Packed onto that layout, the team achieved a transistor density of 9,336 transistors per square millimeter. That density number is the headline most people are missing, because it's genuinely comparable to legacy silicon processes, not some lab toy with 3 transistors stretched across a giant chip. Under the hood, the channel itself uses single-crystal molybdenum disulfide, grown through chemical vapor deposition, paired with contacts made from a semi-metallic material called antimony, specifically chosen to push contact resistance down toward the theoretical quantum limit. The gate stack runs on a high dielectric insulator with a tungsten gate on top. And critically, the chip uses 4 layers of aluminum interconnect wiring to route signals between an instruction decoder, a register file, a multiplexer, and an arithmetic logic unit. That last detail, the on-chip register file, is the architectural breakthrough nobody's talking about enough. Earlier 2-dimensional demos had to fetch data off-chip constantly, which crushed performance. Putting memory directly on the same die as the logic is what let this thing function as an actual processor instead of a single isolated switch. But building one good transistor and building 975 working logic gates that all talk to each other reliably are 2 completely different problems. And that brings us to the part of this story that's actually the real engineering achievement: how they kept the thing from breaking. Every previous attempt at a 2-dimensional microprocessor ran into the same wall. As you chain more and more logic gates together, tiny electrical variations between transistors compound, and at a certain point, the noise margin between a true high signal and a true low signal collapses to 0. The chip doesn't slow down, it just stops working correctly. To solve this, the Nanjing and Huawei team built what they call a multi-level co-optimization methodology, attacking the problem at every layer of the fabrication process simultaneously, rather than chasing one fix. They polished the gate metal and dielectric down to sub-nanometer smoothness to kill interface defects. They redesigned the standard cell layout into a custom 3-row structure to pack transistors tighter and route signals more cleanly. They built a variation-aware logic synthesizer that automatically inserts buffer cells along the chip's most fragile signal paths to restore degraded voltage levels before they cascade into failure. And maybe the cleverest move of all, they flipped the entire manufacturing order. In a normal process, you grow your 2-dimensional material first and then build delicate metal wiring on top of it, which exposes that fragile atomic layer to the heat and chemicals of interconnect fabrication and damages it. This team prefabricated all 4 metal interconnect layers first in a standard industrial fab and only transferred the molybdenum disulfide channel on as the very last step, protecting it from everything that would normally destroy it. That single sequencing change is arguably the most exportable idea in this entire paper, because it's a fabrication strategy, not just a material trick. Now, before this starts sounding like the end of silicon's reign, here's the reality check, and it's an important one. This chip runs in the kilohertz range, while a modern commercial silicon processor runs in the gigahertz range. That gap is roughly 6 orders of magnitude, meaning silicon is still about 1,000,000 times faster. A sister project out of Fudan University, a 32-bit RISC-V processor called RV32-WUJI, tells the same story from a different angle. It packs 5,900 transistors, over 50 times more than the previous world record of 115 transistors for a 2-dimensional chip, and it sips just 0.43 milliwatts of power doing it. Individual test arrays on that chip hit a transistor yield of 99.92%, genuinely excellent. But scale that same design up to a 64-bit register file with 1,152 transistors working together, and the functional yield collapses to just 7%. That's the brutal truth of this technology right now. Small and clever, it works beautifully. Large and complex, it still falls apart far more often than it survives. There's also a deeper limitation baked into both of these chips. They're built entirely from one type of transistor, an NMOS-style design, because nobody has yet solved how to make a reliable, stable P-type version of this material at scale. Real computer logic, the kind your phone uses, pairs N-type and P-type transistors together in complementary MOS or CMOS circuits, because that pairing is what keeps power consumption low when the chip is sitting idle. Without a working P-type partner, these two-dimensional chips leak more power than they should every single time they're switched on. So, no, this is not the end of silicon. Chip architects are blunt about this. Two-dimensional materials are not going to trigger an abrupt collapse of the silicon era. They're a performance enhancer that will get bolted onto silicon, not a replacement that's tearing it down. The honest roadmap looks like this. Within the next 5 years, expect these materials showing up as small auxiliary components bolted onto existing silicon chips, things like ultra-low leakage memory cells. In the 5 to 10-year window, expect hybrid stacks, where a two-dimensional transistor layer sits physically on top of a normal silicon transistor layer in the same chip. True standalone two-dimensional processors, the kind that could run real software on their own, aren't realistically expected in volume for at least another decade. And even then, the most likely first home for them is ultra-low power edge devices, not your next laptop. So if this isn't about beating silicon on raw speed today, why is China pouring resources into it right now, in 2026 specifically? This is where the story stops being about transistors and starts being about geopolitics. Since October 7th of 2022, and again since October 17th of 2023, the United States Bureau of Industry and Security has run an aggressive export control regime aimed squarely at China's advanced chip industry. The mechanism is brutally effective. Extreme ultraviolet lithography machines, the only tools capable of patterning silicon below the 7-nanometer node, are made by exactly one company, ASML, and Washington has made sure China cannot legally buy them. Huawei and its chip design arm, HiSilicon, sit on the U.S. Entity List, which through the Foreign Direct Product Rule cuts them off from American design software and from manufacturing access at advanced foundries like TSMC anywhere in the world. Here's the part that should reframe how you see this entire chip. Two-dimensional materials are so thin that you don't need cutting-edge lithography to get excellent electrostatic performance out of them. A molybdenum disulfide channel that's under 1 nanometer thick can match the electrostatic control of an advanced sub-1 nanometer silicon node while being patterned using older, relaxed lithography tools that China can actually access without breaking sanctions. Roughly 70% of the manufacturing process behind Fudan's RV32-WUJI chip runs on standard, existing legacy fabrication lines already inside China. That's not a footnote. That's the entire strategic logic of this research program. If you can't legally buy the machine that lets you shrink silicon further, you build a different material that doesn't need that machine in the first place. The choice of RISC-V as the architecture for these chips fits the same pattern exactly. It's an open, royalty-free instruction set, which means Chinese researchers can build and customize a processor core around it without paying licensing fees to, or needing approval from, Western standards bodies tied to architectures like ARM. Combine an export control-resistant material with an export control-resistant instruction set, and you get a complete computing stack that doesn't route through a single choke point Washington controls. And to be clear, this isn't a race China is running alone. Just 1 month after the Nanjing and Huawei paper, in June of 2026, a Western consortium of IMEC, ASML, and TSMC demonstrated their own 300mm wafer-scale integration of two-dimensional transistors, hitting a 50-nanometer contacted poly pitch with a device yield of 94%. And they built both N-type and P-type transistors on the same wafer, the complementary pairing that China's chips are still missing. Intel is separately developing its own integration path to slot two-dimensional channels into its existing gate-all-around manufacturing flow. Every major chip power on Earth has independently arrived at the same conclusion. Silicon's successor is two-dimensional, and whoever industrializes it first inherits the next era of computing. So here's where that leaves us. China just proved in a peer-reviewed paper that you can build a real, multi-transistor, system-level processor out of a non-silicon material using equipment you already own, completely outside the reach of the export controls designed to stop you. It is not fast, it is not efficient, and by itself, it is not a threat to TSMC's 2-nanometer roadmap. But it's a working proof that the choke point Washington built around silicon lithography has a side door, and Huawei just walked through it in a research paper. The real question isn't whether this chip beats anything on the market today. It's whether, 10 years from now, when two-dimensional materials are mature enough to matter, the side door China is building right now turns out to have been the head start that counted. If you want to understand how the rest of this chip war is actually playing out, from the chiplet workarounds to the Taylor, Texas fab fight between Samsung and TSMC, that's exactly what this channel covers every week. Subscribe, and I'll see you